of you to the webinar today. I think over the next half an hour or so, a little bit longer, I think, we are going to look at the multicore debugging features of UDE for the AURIX microcontrollers. So I divided the webinar in roughly two main parts. In the first part, I'd like to talk a little bit about the general functions for AURIX debugging, for AURIX multicore debugging without distinguishing between the TC3 and the TC4. And in the second part, I'd like to take a look at some TC4 specifics related to debugging. So yeah, the Infineon AURIX is you see it on this picture here, a typical example of a deeply embedded multi-core system with heterogeneous cores. Such kind of controllers, it's not specific to AURIX, but there are a lot of other devices on the market which follows the same architecture principles. These kind of microcontrollers address application domains which need real-time capabilities and also safety features. And the AURIX itself, it's a typical automotive controller, but it is also used in industrial applications. So what you see on this picture here is the block diagram of an TC3. You see this is a mixture of different core architectures here. For example, we combine the cores of the tri-core architecture up to 6 for the AURIX with domain-specific or application-specific cores based on other architectures. For example, we have a GTM, which is the generic timer module, or we have in the TC3 also the HSM, which is based on a ARM Cortex architecture. The HSM, this is the hardware security module. In the TC4, it looks quite the same, except of the HSM. This is replaced by the SCRM, the security module here, which is right now based on tri-core architecture as well. And we have a new version of the GTM in the TC4, and also there is a new device or a new unit in the AURIX TC4, which is the PPU, which is the parallel processing unit. So of course, such a mixture of homogeneous and heterogeneous cores have a significant impact on the software architecture of the application that should be executed on such a multi-core system. And of course also has a deep impact on the debugging. So basically, in such kind of systems, we find three different, or we can differentiate three scenarios for software partitioning. The simplest one is certainly a single core application. If you bring this onto such a multi-core system, then you can execute several single core applications in parallel on such a system. Each application comes with its own binary file, with its own ELF file, for example, and it's used each of these single core application uses its own core. So there's no or only a minimal dependency between the several applications here. If you look at the debugging, then in most cases we focus only on one of the applications or only on one core at a time. So all the debug actions especially run control, that means breaking the system, single stepping through the code, and so on, should be performed only on that specific core. The opposite case is a monolithic application. All the tasks and functions are distributed across all the available cores. We have close dependencies between the cores, and we need synchronization of the debug actions. So all the cores must be stopped synchronously, for example, if the application hits a breakpoint or if you do single stepping on one core. So otherwise you would get an inconsistent application state immediately. And then we have, of course, a mix of both corner cases, or we have different code bases and binaries for different cores. For example, for the main cores and the GTM or the PPU in the case of the AURIX TC4. And for this case, there may be the need to perform debug actions only on a subset of the cores. So we need a kind of partition debug synchronization. So, and yeah, how this is handled in the UDE debugger. And before I go into the tool, let me show you what you can't see here in this webinar. And this is a picture of the hardware setup that I use for the webinar today. I use a standard Infineon tri-board with an AURIX TC4. And as a debugger hardware, which is needed to get access to the tri-board with the AURIX, I use the UDE 2 Pro of our universal access device family. This is the base device in this family. It's dedicated for debugging. You can't do tracing with that device. There's no trace memory inside, but if the device, like a emulation device of the AURIX, comes with its own trace memory, then you can do traces as well. But there's no trace memory in the device, so you need a on-chip trace memory. Okay, but that's not the topic for today. Tracing, what you see here on this picture is also that the UDE 2 Pro is connected using USB to my PC. And we have, for the connection to the tri-board here, I use the Infineon JTAG DAP target adapter that is part of the hardware setup of UDE. The adapter is the only, it's the device-dependent part in this hardware setup. The UDE 2 Pro can also be used for other architectures like Cortex, ARM Cortex, or maybe RH850 from Renesas and so on. To connect to the devices, you need this a specific adapter and, of course, a architecture license in UDE. Okay, for the TC3, it looks the same. And also all the debug features, the basic debug features from Multicore are the same. So I show this on the example of the TC4, but the same functions are also available for the TC3. There's no difference for the basic debug functions. Okay, then let's jump to the UDE. And I already opened the debug tool, and the first thing what we need to do is to set up the debug session. We call this the workspace, and that's quite simple. A few clicks are needed. You can use the menu here, or you can use also the toolbar buttons as you like. I use the menu for now, and I select from the file menu the new workspace command. The workspace is a file on your PC, so I have to select a folder for that and a name for that. I take TC4x, which is the device on my desk here, and then I need to set up the target configuration, which describes or which contains all the information needed to access the device using the debug interface, and set some specific register settings for debugging. You can browse for a already existing target configuration. It's also a file. If you start with UDE, then I recommend to use the default setups and default pre-configured target configurations. We have a complete list here of all the supported microcontroller architectures. So I look for the TC4 from Infineon. We have a TC4x starter kit here, and then I open this and select the tri-board that should be connected using the debug interface. Finish, then I save the file, and then I can select the file or the target configuration and press OK. Then UDE asks me which cores I want to see in the debugger. So by default, we see all the 6 main cores, tri-core based cores here. The others are disabled right now. And for the first steps we do, this is completely fine. So we leave it untouched. So we want to debug a application using all the 6 cores. So the message window indicates that we have successfully connected to all the 6 cores. In UDE internal, you have so-called core debuggers. Each core debugger belongs to a specific core here. So you see for each of the 6 core debuggers, we have a successful connection. You see also the status of each core debugger here in the toolbar. You see these indicators, and you see also that all the cores have its own color. So all the windows that belong to a specific core have this color in UDE. So you have a good overview of your application and your debug session here. Then, of course, we need an application that we want to test or to debug. So the next is to load a program. You can select also using the file dialog here, a ELF file, for example. And then this window pops up, which is the loader dialog, which allows you to change or to specify which core should load the binary into the RAM or into the flash of the device, and for which cores you want to load debug symbols. In the default case, we load the application using core 0. In the AURIX, this is the only one which is active on reset. The other cores are inactive right now and has to be waked up by the main core, by the core 0 here. So that means we check the blue checkbox here, which loads the binary into the target device, into the AURIX, and we check the green checkboxes here to load the debug symbols provided in the ELF file into the debuggers, into the core debuggers in UDE. I skipped this for the moment because I'd like to show you a different way to load the application. Another way to load the application is to load only the hex file, which contains only the binaries. And then, of course, we have no debug symbols here available. The debug symbols are then in a separate ELF file. and you can check the hex-elf option to load a separate elf file. If it's has the same name as the hex file, then automatically UDE automatically loads this elf file, or you get a UDE requests you to browse in the elf file that provides the appropriate debug symbols. Okay, now we can load this application. We will be asked for some source files because the application was not compiled at this PC. It was compiled on another PC with another location of all the source files, and the ELF file contains at the moment the wrong path information for the source files. But we can skip this here right now. We will load the source files another way in a minute. So we cancel that. We have also canceled that request for the source file, and then the Flash tool gets opened. So the Flash tool allows you to program the flash memory. We program all. It's quite fast because the application is very small. Then we can close that. And now we want to tell UDE how to find or where to find the correct source files. And for that, we go to the config menu, debug server configuration. And from the left side, we can select source code, the source code setup here. We have two buttons on top. The right one, the aliases. If you open that, we find the two files that UDE already requested. We skipped that, so UDE, don't try to open that again. And it is a good idea to clean this up. Right now, we can delete all the settings here or the entries. And then we open the path management and define path replacement rules. So we know that in the ELF file, we have paths given where the source files are, where UDE should look for the source files, but this is a folder that not exists on my PC right now. So we define a path replacement rule in that case for these two paths here. First, the deboard path. We replace that one with a new one. I look for the file folder on my PC. And second, also for the source paths of my sources, which is that one. Okay, and then I can start debugging, and if I have made it go, everything is running right now, and if I hit the break button here, then automatically the files gets opened. I can open now other windows, for example, a watch window where I browse in some variables. Here I can use, I can type in the name here, and it is filtered. I can enable a periodic refresh here. If I activate or I run the application again, then you see the values are updated at runtime. Or I open now a peripheral register window and browse for a register, maybe a GPIO register that controls the LEDs on my board. I can also here enable the periodic refresh, and then I can see all the the values changing that controls the LEDs on my board. Okay, so you can set up all the windows, all the visualizations that you need for debugging, and start your debug session. You can save this debug session here, this workspace, and open it tomorrow again, and you can continue your work where you left it, or you can forward the workspace to a teammate, for example, a test engineer, that he can do some tests on the application. I have already prepared the workspace to show you some more features here. I opened this, so we close this, we save this workspace, okay. And I open the next one, which loads the same application. This is the same application, same setup. Press OK, then the Flash tool gets opened again. I can reprogram the contents, but I know that this is the same application. To make sure, I verify the Flash contents, so we have no differences. It's the same application, and then I can make it go. We see some variables here in watch windows. You see the colors of the cores, and you can see also the source code here. I have put this in different containers here in the UDE to get a better overview. You can use, of course, multi-screen or multiple screens. For example, if we open another window for the source code, then I can take this window and put it on the outside of UDE or a second screen or something like that. Let me do also open a watch window for the Core 2. Browse in a local structure and enable the periodic refresh, that we can see what's happened on the core. And then I'd like to open always, so a breakpoint window. Okay, there is no breakpoint at all at the moment, but we like to break our application right now, for example, in a function in the core 1 worker core 1. I open this, and then I can set a breakpoint here on this blue bubble. The blue bubbles mean for this line of code there are addresses available, so there are real machine code instructions. If there is no blue bubble here, no breakpoint can be set on that line because there is no code. I can set the breakpoint here, or I can set the breakpoint also in the symbol window here. I set a breakpoint, and we instantly hit this breakpoint, and you see that by default all the cores, you see it on top in the core indicators, or by the yellow line here in each window, all the cores are stopped instantly. So this is the already mentioned the debug synchronization. By default, all the tri-core cores, all the main cores are synchronized for debugging. Now you can, for example, do some single steppings here, and you see I do single stepping in core 1, and you see all the other core steps as well. And these are not always single steps, depending on the clock settings. This could be a partial single step, a stepping in machine code, or you can step over several machine code instructions if you do a single step in, for example, in the core 1. Okay, so if you like to break this synchronization, And then you have to make sure that all the cores are stopped. And then you can open from the menu config the Multicore run control configuration. And there is a group defined which contains all the cores. And all the cores in this group are synchronized for debugging. So we can remove, for example, the core 1 from this group. And if we start right now the core 0, so I press core 0 here to activate or to put a focus on that for debugging, then I can make it go. We see core 0 is running, core 2, core 3, core 4, core 5, which are the cores in the run control group. All the cores are running, but core 1 are still in the halted state. Now you can do some single steps here without influencing all the others, or you can disable the breakpoint and make it go here. Then all the cores are now running. And if I enable the breakpoint in core 1, then only core 1 stops and the others keeps running. To bring back the core 1 into the run control group, as said already, we have to break the complete system. And then I can open the Multicore Run Control Manager, put the core back, and then switch off the breakpoint, start everything. Everything is now running. If I enable the breakpoint again, then everything is halted asynchronously. That is the concept of the synchronization in UDE of all the cores. If you want to disable the run control synchronization completely, then you can remove all the cores from the run control group. One limitation for the AURIX, core 0 has to be always in the run control group. So to disable all, it is a better idea to check this box or uncheck this box here, which disables the run control group completely. Okay. Breakpoints are always core specific. That is important to know. So if you set a breakpoint in core 1, only the code that is executed by code 1 will hit the breakpoint. If you have shared code, then it gets a little bit complicated, obviously. I switched to another perspective in UDE, which shows you a function which is shared and executed by all the cores. So if you look, for example, here in we have a mixed mode that shows you the assembler instructions or machine code instructions. And if you look at this function here on core 0 and at core 1, you see it's the same function at the same address. So it is a real shared function here. As said before, breakpoints are core specific. That means if I run the application again and set the breakpoint here in core 0, then only in core 0 the breakpoint is hit, and never in core 1, core 2, and so on. So maybe you set the breakpoint here in the core 1, then the core 1 breakpoint is hit as well. But this would be very annoying if you want to do this for all the 6 cores. So that's why in UDE we have the concept of multi-core breakpoints. You can change a single core breakpoint to a multi-core breakpoint by tick this multi-core option here. Then you see that the icon has changed. And if we do some go commands, then you see, okay, now we are stopped in core 2. If we do a go again, then we are stopped in core 0, and so on and so forth. So this is a very nice feature, or a very simple way to define a breakpoint in all the cores. Technically, these are single core breakpoints. You see it here in the breakpoint window. If I unfold this multi-core breakpoint, that on all the cores, a single core breakpoint is set. And this is also correlated to the defined run control group. So the multi-core breakpoint is only set to the cores that is which are part of the run control group. Okay. Yeah, then we can leave UDE for a moment and go back to the presentation. Right now, I'd like to come to TC4 specifics, as I promised at the beginning. Maybe this is interesting for new projects. Maybe you are already using TC4, or you are thinking about to use TC4, maybe because of the special functions that TC4 has in comparison to the TC3. One special function related, or a specific on the TC4 is the possibility to debug the GTM. The GTM is already present in TC2 and TC3, but with the TC4 we have some new features related to debugging. So the GTM itself, it's a generic timer module, a Bosch IP that was designed to support timer applications. Maybe you need some PWM generation in your application, or want to do some signal filtering for motor control, etc. Then the GTM is a very powerful unit that can be used for such applications. The GTM contains many different modules for different purposes, and that includes also a module called the multi-channel sequencer, MCS. There are several of them in the GTM. It depends a little bit on the device that you have, how many of these MCS exist. And the MCS can execute channel programs. So that provides a kind of programming capability. So you can write channel programs that are executed in a round-robin manner by the channel by the channels. There are up to 8 channels, or there are 8 channels in each MCS, so you can execute up to 8 channel programs. And these channel programs can also be debugged in UDE, because for that we have code. But as I said before, there is a difference between TC3, TC2, and TC4. And debugging, that means that means run control, setting breakpoints, stepping through the code, is only possible with the latest version of the GTM, which is the version 4.1. For older versions, there is no hardware support for debugging at all. And for those devices with the older versions, only trace can be used to debug the GTM code execution. But it's not the topic for today. I'd like to show you how to debug the GTM latest version on the TC4. And on TC3 and older ones, there is not a GTM 4.1 available, so only trace can be used for those devices. Okay, the MCS code cannot be loaded directly into the GTM memory. That's why the code has to be linked into the main application, into the host application, and also the host application has to start the GTM. And then during this startup process or this boot process, the GTM code is copied into the GTM RAM from the host application. That means the host application contains both the binaries for the tri-core main cores and also the code for the binaries for the MCS channel programs. If you program the GTM MCS channels using a compiler, there are several compilers on the market, and then you can create, of course, ELF files that contains all the debug information, and these ELF files can be loaded separately into the UDE to provide all the functions, all the source code, and all the symbols that you need for debugging. And that I'd like to show you right now. We again create a new workspace, which we call GTM. We take the same target configuration, and now we tick the GTM checkbox here. So that means we want to have a GTM core debugger in UDE. And we have an application that is running only on core 0, so it makes no sense to check the other cores. Okay. Once we have a successful connection, we can load the GTM example program, which contains both the binaries for the host core, the core 0, and also the binaries for the GTM. Here again, we have to flash the application using core 0, and we have no simple information for the GTM in this ELF file. So it makes no sense to tick here on the GTM core debugger any of these checkboxes. But we want to load symbols from several additional ELF files. So we add another ELF file, or basically 4 of them, because for each MCS that is used, we have a separate ELF file. I can select all of them at once, and then this window pops up. This is called the relocation dialog. Because of the that we copy the GTM code by core 0 into the GTM memory, the debugger needs to know where the code is finally located in the GTM memory. UDE does some assumption of this relocation, but these assumptions must not be correct. So, or it's not always correct, and so you have to double check if it's okay or not. And in our case, so we get 4 times this dialog for each MCS unit. So we have 4 MCS ELF files, and so we have to double check all the 4 MCS units. We look for the code and data mappings here, and this is the region, the correct region for the MCS 0. I press OK. This is the correct region for the MCS 1, and so on. And that's okay for now, but you have to check that. And then we can check the symbols checkboxes here to load the symbols, and then we can flash the application, and then we can start debugging for the main core. But by default, the run control for the GTM debugger is not active because of the different types or different versions of the GTMs. So you have to do an additional configuration step. You activate the GTM debugger by clicking on the toolbar indicator here, you see on the bottom line here that the GTM is now the active debugger or the debugger in focus. Let me go to the config and target interface. Then make sure here on the window title is the GTM visible, and then we can check this box, which enables the run control for GTM 4.1 devices. At the moment, this feature is only active if you reload the workspace. So we close this, we save the workspace, and we open this workspace again. And with that, right now we verify we can start the application. Core 0 is running, the GTM core is also running. We can then open, for example, a channel program. These are quite simple here, and set a breakpoint, for example, in the GTM, in the MCS 0, channel 0. We hit the breakpoint. We can do some single steps. Step into, for example, and do debugging the GTM code. You see that the Core 0 is still running. That means we have no synchronization between both the Core 0 and the GTM. You can, of course, use the run control management to synchronize both. You can add the GTM to the run control group, and then we can disable the breakpoint and start the execution again. And then if we enable the breakpoint and the breakpoint is hit, you see that also the Core 0 is halted as well. You can then do some single steps. You see also Core 0 do some steppings, and so you can do the GTM debugging. Okay, time is almost up, so I'd like to come to an end and have a look at the other module, which is, or the module that is new in the TC4, which is the PPU, which is also a other architecture, or based on another architecture. It's based on the Synopsys Arc EV. And this PPU is intended for data processing and can support, or is dedicated to support AI applications. From the debugger usage perspective, the PPU is handled similar to the GTM. So again, the binaries of the PPU are linked into the host application, and the tri-core course copies then the binaries into the PPU memory and wakes up the PPU. And again, we need to flash via the Core 0. You see it on the screenshot here on the bottom. And then we can load separately the PPU core or the PPU symbols into the PPU core debugger in UDE. So it's quite the same. I do not show that here in this webinar because of the time. But if you are interested in PPU debugging, then you can contact our support team as well. Okay, that ends the webinar for today about debugging of TC3 and TC4. I'd like to thank you for your attention.